Hey guys, it's Mystery Man. In the last video, if you've not seen it, I've calculated the sine and cosine. But now I've brought something else to the table today. As you can see in the title, I will be showing you how this machine behind me can calculate log base 10 and natural logarithms. Now, obviously I had to restrict to how many decimal places it can calculate them. So when we're dealing with the result, it's always going to be accurate to these two decimal places. And the very last one will be mostly correct, but there's a rare chance it's not. It just really depends on what number you input, and that's because my hardware here is very restricted. There's only 10 decimal places here, and what happens is when I shift, sometimes the numbers will chop their data off, so it's not going to be obviously a perfect shift, but it's good enough to get a very accurate result for at least this game. Now, if I wanted to, I could have made the result more accurate, but the problem is speed. It gets slower. And I'm going to show you what its speed is by calculating the log of 16 first. So I plan to do that first. So since we're in BCD, each of these 4-bit groups represents a decimal number, so the system that we use. So if I want to do 16, I would put a 1 in the tens column, and this is just 1, 2, 4, 8. In binary, each bit doubles, but we're grouping them in 4s so that we can represent 0 through 9. So we've got 1, and then if I turn on these two, this will be 6 in binary, so if we combine them, that's 16. And now this is the clock right here, so you can measure the clock speed for yourself just by looking at that. Obviously not the fastest thing, but that's because I'm dealing with a 40-bit word, so it's actually pretty fast for what it does. So yeah, we're going to watch it calculate the logarithm of 16, and I'll show you what I'll show you what the more accurate result is. That's the more accurate result, but we're probably just going to see 1.20 as our result. So, yep. Did I mention this thing wasn't the craziest thing in the world in terms of speed? Yeah, I think I did. But it's pretty fast for 40 bits. Gotta say it's pretty fast. So the light right here, when it turns on, means the calculation's complete. So we're actually almost done. It doesn't take long to do numbers that are related to base 2. So, yeah. Will you turn on, dummy light? I don't know. Oh, it did, yeah. Okay, there's our result though. So, yeah, I inputted... Well, I thought I inputted something, but it's gone now. Oh, I did, but I didn't type it. So I said that the log of 16 is approximately this value, and as you can see, we've got 1.20, which is perfect for this set here, or in this case, this desired accuracy. So now, I do have some help that will speed this machine, overclocking it. We can change the tick rate to something pretty high and just see what the result is faster without me doing weird stuff, so that's great. Okay, so now we're going to try the log of 5 as our next test number. So I just put 5 here. That's the decimal number, and there's like 7 decimals after that. But I put in 5. I reset the machine, hopefully. Let's just double check. Sometimes I forget this and I don't get it. Yeah, I reset it. That's the reset button. Okay, so I'm going to press this. And then once I get to the other side, we'll just use the tick rate thing to speed up this machine. So /tick rate 200. And, oh yeah, check that speed out. So good. I love that. And we are done. So the answer of the log of 5 is 0.69. And the actual result is approximately 0.698, so on, so on, so on. So it's good enough for this set of values right here, which is beautiful. Very cool. So I will go ahead and turn that off, and we're going to test the next number, which is 77. Again, I just pull these numbers out of a hat, basically. Wow. My mental hat. So there's 77. That's 7 in binary, and another 7 in binary, but represented, in their decimal places. And now I will just press this button and hopefully go over here. Boom. Check this out. 1.8. We're going. Now I'll show you what the actual result is up to 3 decimal places. So that's the actual result up to 3, and we got 1.88. So yay! We got the right answer again, which is great. Very cool. Yeah, sometimes it'll only be these 2 that get the correct result, but I'm glad that all 3 did this time. Depends on what number you input, again, because of my shifting and adding, and also the table that I have. It uses a couple of things to make this work, so. Alright, so for the last, or that is the last decimal value, guess what? Now we're going to do natural logarithms. Yay! Go ahead and get that calculator out, because now we're going to really do stuff. I guess you're already checking with me. That's good. We're going to do the natural log of 88, so just this in your calculator. Alright? That's what we're going to do. So there's 8 and 8 in binary. And before we start the calculation, I have to switch the mode to natural log. So to do that, I just flip the tables here. Now we're using these 4 instead of those. So as you can see, this isn't enabled, and it basically just uses values there, and either there goes there. So we're going to flip it to natural log mode. And then I am going to go ahead and just input the clock there. And this is only going to be accurate to those 2 decimal places, because it's obviously a little quirky when you use the natural log. Alright, so we're expecting a value of 4.47, but as you can see, we only get 4.4, and the last number is not perfect. So when you're using natural logs with my current setup here, it's only going to get these 2, and that's actually perfectly fine in my opinion. The fact that I can get an extra base out of that's actually practical, is actually very cool. So that's cool. So we got 4.4, which is pretty good for me. So here's what we should have got, but obviously we didn't get there. Alright, now we're going to do the natural logarithm of 270. So I will just go ahead and do this. And now I'm going to go ahead and put 270 in here. So we'll put 2 in the hundreds, 7 in the tens, 0 in the ones, and let's just calculate it. Again, we're running this at 200 ticks now, so it's not 20 ticks. That's why it's so fast. Okay, so I'll show you what we're expecting. So 5 point. Here's the actual result up to that many places, but we're not going to obviously get like that. So as you can see, we got the 5.5, but the last number is obviously incorrect, and that's expected. So good, we got the 5.5, which is really nice. So yeah, and now we're going to do one more value, which is the natural log of 9. Again, I just pulled these numbers out of my mental hat. I didn't have these numbers planned at all, so I might add an extra one just to spice things up with a 0.5 in there, so you can see that it'll actually also be okay. It doesn't really work when you do 2, though. It only works when you do this because of the range of shifts I have, so we are limited. So we've got 9 there, and now I'll just turn on the calculator. I might build a smaller machine in the future, then I'll make a world download. I'm not really confident to make a world download for you guys yet because it's a little complicated, and I actually have a cooler project in mind that you guys will enjoy. Okay, so here's what we should have gotten from the natural log of 9 up to a certain point. We should have gotten 2.19, but obviously only to these places, so we got 2.15, and yeah, the last values they threw in the towel and they're like, okay, I can't do this anymore. So it's just 2.1 natural log, and I'm pretty satisfied with that actually. So yeah, and that's basically it. So now we're going to move on to the part where I actually explain how to do logarithms by hand. Yes, you can even do logarithms by hand. You can basically put bets against your teacher if you're confident enough and show them, yeah. I'll show you how to do it though. So let's hop on to the next clip if you're interested. Alright guys, so this is the part where I explain about the tricks that we can use with logarithms and also the way we can kind of apply them. So right here I just made a table of log base 10. If you don't know, I'll show you what log base 10 really looks like. So let's just, yeah, I didn't do this all that smart. That's okay, we're getting through this together. So when you see this in math class, what they're really trying to say is this. So right here, whenever there's a certain number base we're using, they'll put it down here. In this case, this is base 10. And then whatever you put in here. So instead of writing the base 10 for the standard log, we just write it like so. That's basically all. That's all that's going on there. Now, the next question is, what is a logarithm? Well, a logarithm is the inverse of an exponential function, or it basically equals the power. So let's say I had an exponential function. In this case, we could say this is 10x, like so. I believe that'll work, yep. So 10 to the x, and then over here, I could just have log of x. And the only thing that's different between these two functions is that the x and y coordinates have flipped. They're obviously not the same, but their x and y coordinates are flipped. That's all that's different about them. So if I had, let's say, the number 10 right here, not 10, yeah, right there, 10, and then I had 1 there, this is basically saying, well, if I input 1 up here, then we get 10, because 10 to the power of 1 is just 10, right? So that's what we'd get. However, if I put the number 10 in here, then we get the result of 1. So if I put 10 in there, we would get 1, because the logarithm of 10 is 1 in base 10. And that's because we are trying to get the power in this case. So this 1 is equal to the power of what we selected here for the x. That's all we're trying to achieve with the logarithm. Okay, so that's what's going on with the logarithm in a very basic explanation. I can't really go into it too far because it's not too important right now. So why did I make a logarithm table here? Well, since logarithms are a way to get the power of some number we put in this graph-based thing that we just saw, you know what I mean, we just went over that. Since these are actually the powers, we can do some funny things with them. So if we were to add these two numbers together from log of 2 and log of 3, that's the exact same thing as doing 2 times 3, and you're going to see exactly why. So I'm going to actually just try to do 2 times 3, but I'm not going to actually multiply. I'm going to use addition only. So I'm going to go ahead and do 0.31. Now this is obviously set to 3 decimals. You probably want more to be very accurate. So 0.31 and then 0.477. So if I add these together, we're effectively going to multiply our result, and you'll see why. So our result is 0.778, and if we look at a result from the table that has 0.778, look what it points to. The number 6. And 6 is the result of 3 times 2. So by adding two logarithm values, I can remove the logarithm and get 6, which is awesome. So that's a really cool thing. I'll go ahead and demonstrate this with another one I mean, so that we can actually see that being the case in our situation. So let's do 5 times 2. So now this won't be perfect because it's rounded 3 decimal places, but you'll see that it'll converge to the correct result, and I hope that I can get this point across. So if I do 0.301 plus 0.698, we're going to get 999, and this number will just be 0.9999 continuously, because it's actually eventually going to converge to this number 1. So if we recognize that it's converging to the number 1, then we could say it is 1. So if we now point back to this, it is 10. So when we did 5 times 2, it's actually 10. But by simply adding two logarithm values together, I can also get 10. Alright, great. So now that I've kind of shown you that cool thing about logarithms, you can also do division with them as well. Why not? You just do subtraction with two logarithms. So I'm going to go ahead and do 9 divided by 3 simply by subtracting the value. Now, it's probably going to be very close to this result right here, but not exact because I rounded it to 3 decimals. As you could tell, yeah, so keep that in mind when I do my little mini example here. Okay, so what I'm going to do is I'm going to have to borrow an 8 here. I'm going to have to borrow 14 because I first turned that to 15, and then I have to change it to 14. Then this is 14, 7, 7, 4. Oh, would you look at that? I found 0.447, which is 3. So if I did 9 divided by 3, it's 3. And all I had to do is do this number minus this number to get 3. So there you go. If I remove the log, then we would get the divided number of the two. So if you're very crazy, you could actually just make a lookup table of logarithms for your redstone or software-based machine and do division and multiplication by adding and subtracting. But that would require a pretty big lookup table, so keep that in mind. So now that we know that we actually can do this, how did my logarithm machine actually calculate logarithms? And that's where I'm going to get to the next point now. Alright guys, so right here I've prepared a little demonstration of how the algorithm works. I've pre-calculated everything that should happen, and we'll just walk through it together. So in this case right here, I've modeled the calculation for the log of 5. So what the algorithm does is it first refers to this log table value, and it'll add it up here. So these are all the accumulated values throughout the entire sequence of this algorithm. So The first thing the machine does with a separate adder is it does 2 plus 0 equals 2. And then there's a conditional check called if A is less than B. This result right here is our B, and 5 right here is the A. So right here we're saying is 2 greater than 5. Since it isn't, we keep the same log value and we accumulate it. So all these values are accumulated as the machine goes along. So now we're doing 2 plus 2 equals 4 because I took the result and put it in the B value because we were allowed to do it. And that's all we're doing. We're just moving into B. And then I do 2 plus 2, which gives me 4. I check if 4 is greater than 5, and it's not. So I can add the value again. And then I can now shift this into the B and check is 4 plus 4, well, we know that 4 plus 4 is 8, but now we're going to say is 8 greater than A. Since 8 is greater than 5, what it does is it backtracks this value to 4. And then what we're going to do is we are going to switch the table to now focus on this value right here. So now these values right here are the logs of this, all right? So we already have our accumulated answer up here, and now it's being added to this now, all right? So now I take the 4, I put it in here, but you can see now we have a 0.4. Why is that? So if you remember from earlier, I showed you the trick where you can add 2 logs together to get the multiplied result of this. I am doing the exact same thing with small logarithm approximations. However, we're doing it by shifting and adding. So when I'm doing 4 plus 0.4, what I'm trying to do is actually this. I'm trying to do 4 times 1.1. And since I'm multiplying this, I can actually just add the logarithms over here on the side. But since hardware multipliers are expensive for time, or well, they're just expensive in general. Since they're pretty expensive to use, it's actually faster just to do a shift and then add, and that does the exact same thing. So we got our 4.4, and then the algorithm checks if 4.4 is greater than 5 in our case, and it's not. So we add that log value. I take 4.4 in this register, and then I take the result from this part, and I shift it right here in the B. So it just shifted once again. Now it's 0.44. And we get 4.84. And then the algorithm again checks, is 4.84 greater than 5 in our case? It's not. So we can go ahead and add this value now to the accumulating log value. I could take the answer from this guy and shift it over. And then I just add it to this guy. And now we get to our section where it's going to switch the values again, because now it's saying that B is greater than the 5 in our case, because it's 5.324 and our target number is 5. So since this happened again, we discard this. And then I take this value, and now I'm actually shifting it twice because now we're using this log table. So whenever we come across the flag for I went above, it removes this number. Basically, it shifts over, and it also now does 2 shifts over. So now we're doing this. Now we're doing this, but we're using shift logic to get rid of the multiplication. Okay, so I take the result from previous answer and I am now putting it in the B, but we're shifting twice now. And I get 4.8884, which is still smaller than A. So I just take that result from there and I shift it over twice. And then I do the addition. It's still under 5, so again I take the result, I shift it twice and add it to that. And the result is still under it. And then this final part right here, I take the result, I shift it twice, I add it to this number, and look, it goes over 5. And this is the point where the machine stops. When it runs out of log values and the values to determine the amount of shifts, it stops. And whatever was accumulated in the logarithm adder, there's two separate adders. There's one BCD adder and subtraction cell to do the adding of these and conditionals and the shifts. And then there's a separate adder, the one you saw on the top of the machine, that does the logarithm approximation. So this is the accumulated sum of all of our nonsense going on here. And as you can see, our result is 0.69. Now, with this amount of data right here, you're always going to get the result accurate to that amount. However, since the log of 5 was a small value, it actually was able to get it pretty accurate. So yeah, the more log values you have here and the more shifts you do according to this model, you can basically keep converging to the correct result, although it'll take a lot longer. So I hope this demo helped in some way. If you're planning on building a logarithm calculator or some program for it, I wish you the best of luck. And I guess I'll see you guys in another one.